100,000 times weaker than the strong force. When we look at the weak force at its natural scale, we see that it's actually similar to electromagnetism, and that was the beautiful insight that allowed for electroweak unification. We'll talk a great deal about this in Lecture 8, but for most practical purposes, the weak force acts extremely weakly. Then there's gravity. It has an infinite range like electromagnetism, but at the femtometer distance scale, gravity is something like 10 to the 40 times weaker than the strong force. That's a 1 over a 1 followed by 40 zeros. I say something like because you get a different answer if you're talking about the gravitational force between two protons, two electrons, or a proton and electron, but the 10 to the 40 number gives you the right message. Gravity is crazy weak, and indeed, gravity is so weak that we've never figured out a way to study it on these super small scales. If we tried to study it down there, the measurements would just get swamped by the effects of the other forces. So gravity is not covered by the standard model. The Higgs field is a bit different because what it does is give mass to particles. So it's not a force in the way that the others are, and you can't talk about it in quite the same way. So I can't tell you how its strength compares to the others. This is one of the times where the word interaction is more apt. The change that the Higgs field causes is to turn massless particles into massive ones. With the introduction of the forces, we're now ready to begin to get a handle on the pieces of the standard model. Let's start with the quarks. There are 6 different types of quarks. Physicists say flavors of quarks because, well, particle physicists do like cutesy terminology. The quarks have kind of silly names, which are up and down, charm and strange, and top and bottom. The up, charm, and top quarks have an electric charge of 2/3 that of a proton. The down, strange, and bottom quarks have an electric charge of -1/3 of a proton. The up and down quarks are found inside protons and neutrons. A proton contains 2 up quarks and a down quark, while a neutron contains 2 down quarks and an up quark. You can check that the electric charges make sense. The up quark has a charge of +2/3, and the down quark has a charge of -1/3. So thinking in the context of charge, the protons up, and down is 2/3 plus 2/3 minus 1/3 equals 1, which is the charge of a proton. For the neutron's quark content of up, down, and down, we see 2/3 minus 1/3 minus 1/3, which is 0, and that works out great. All of the quarks experience the electromagnetic force, but they also experience the strong force and the weak force as well. While the up and down quarks are found in stable atoms, the other 4 quarks are unstable and disappear in the blink of an eye, far shorter than a second. In fact, the longest-lived one disappears in about 100 millionth of a second, and the one with the shortest lifespan exists only a half of a trillionth of a second. So the only way to study them is to create them in particle accelerators, which is what we do. All 6 types of quarks have been discovered. The quarks have very different masses. The up and down quarks have very small masses, less than 1/100th of that of a proton. The strange quark's mass is higher than the stable 2, maybe 20 or 40 times higher. The other quarks are porkers by comparison. The charm quark is about 30% heavier than the proton, and the bottom quark is more than 4 times heavier than the proton. But the king of the quarks is the top quark, weighing in about 185 times heavier than a proton, or about as much as an entire atom of tungsten. The top quark was discovered in 1995 by, well, me. Okay, of course it was me and 800 of my closest personal friends, and they all had something to do with it. But, don't tell my mom. Somehow she got the idea in her head that I did it myself, and, well, I'm sure you understand. So the quarks are the heaviest particles, most commonly found in the nucleus of atoms. The leptons are different. For one thing, they're generally lighter than the quarks. Leptons don't feel the strong nuclear force, but they feel the weak force, and their interaction with electromagnetic force is mixed. There are 2 classes of leptons. The first row includes the electron, the muon, and the tau lepton. They all carry electric charge, and so we'll call them the charged leptons. It's simplest to think of the muon and tau lepton as just heavier cousins of the electron. The electron weighs about 0.05% that of a proton, while the muon is a smidge heavier than 10% of a proton. And the tau lepton is just shy of being double the mass of a proton. the quarks, the heavier charged leptons decay very quickly, with the longest lived one existing only a millionth of a second or so. So, if you want to study them, you need a particle accelerator. The second row of leptons are called neutrinos. They don't have electric charge, so they only experience the weak force. Because the weak force is, well, weak, it means that neutrinos can pass through matter without interacting. Neutrinos are produced in nuclear reactions